This exercise is on exponential growth and decay. It's an extension exercise. I put a little e there to denote that. So exponential growth and decay is when the rate of change of a quantity is directly proportional to the current quantity. So if you've got lots of it, it's going to be growing or decaying really quickly. If there's not very much of it, then it's not going to be changing very much. So you can think of things like a population. If there's only like 50 people in your population, then that population isn't going to grow very quickly. But if you've got 50 million people in a population, that population will keep growing really, really quickly because there are a lot more people to have babies, basically. So the rate of change, remember, is the derivative. So the rate of change, or the derivative, is equal to some constant multiplied by the number in the population. Now, if it's growth, if something's growing, that k is going to be a positive number because it's going to increase. You're multiplying it by a positive number to make it grow. If the k is a negative, then it's decaying. The rate of change is negative. It's decreasing, it's decaying. Now, in year 12, we will learn how to integrate this formula. But for now, we're just going to show basically that this does work in that formula because we haven't learned how to actually solve it in reverse yet. So what I'm going to do is differentiate this. So remember, we need to multiply it by the derivative of the inside, which is the k. So the derivative is k times, and the derivative of e to the x is just e to the x. So that's the chain rule. Now we can see that this whole thing right here is equal to n. So the result of that is that the derivative equals k times n, which is this formula. So anytime you get a question that's talking about exponential growth or decay, or that says the rate is proportional to the quantity, this is the formula that you're going to be using at this point. The second bit here is show that A is the initial quantity. So the initial quantity just tells us what is it when t is equal to 0. So if I put t equals to 0 into my formula, a to the k times 0, k times 0 is 0, e to the 0 is 1, so that equals a. Now you will get questions that say find the initial quantity. You must show that substitution of 0. Don't just write the number of a without showing by substituting t equals 0. Let's look at this example where we've got the population growth of rabbits. So we're told that in a particular population they're growing at this, according to this formula, where t is in months. Show that the initial population is 1500 is the first part. So that's exactly what I was saying. T equals 0, n equals 1500 e to the 0.02 times 0, which equals 1500. Part B is to find the population after 2 years. Now it's really important to see what t is measured in, and t we were told is measured in months. So be really careful here. It's asked 2 years, but we do need to keep in mind that that is 24 months. So we're substituting 24 into the formula. So 1500 e to the 0.02 times 24. Now we'll show you entering that into the calculator. So 1500 and then shift the log natural button, 0.02 times 24. So the population is a little over 2,424. I'm just going to round to the nearest whole number because obviously you can't have part of a rabbit. So it makes sense to use the nearest whole number, 2424 rabbits. At what rate is the population increasing after 2 years? So of course, if it's asking about rates, you need the derivative. So we could actually technically just say dn dt equals k times n. So k is the 0.02. We could go 0.02 times 2424, but I'm just going to prove that that is the answer here. So dn dt is the derivative, so 0.02 times 1500 e to the 0.02t, and 2 years, so 0.02 times 1500 e to the 0.02 times 24. Okay, and you can see this bit here is exactly what we just put in our calculator. So if you just go times 0.02 from your solution, the answer is about 48.5. Now it is a rate, so we do need to give units, and our units here, because t is in months, the units would be rabbits per month, which for a rabbit population is probably actually quite slow, but almost 50 new rabbits being born every single month. Part D is to sketch the graph of the population. You'll notice that my axes, I've only done positive numbers because you're only going to have a positive number of rabbits, and time can't be negative. So time goes on our horizontal axis, and n, the number of rabbits, goes on our vertical axis. Now, we did find out that at the very start there were 1,500 rabbits. I'm going to mark 1,500 right here. And then we also found out that after 2 years, so somewhere over here I'm going to put 2 years, it doesn't really matter where. I'm going to put 24 actually because time is in months. And we found at that point there were 2,424. So if that's 1,500, that'd be about 3,000 there, so I've gone up a bit too high. So a bit lower than that, so around about there. It is an exponential curve, so I'm going to draw it like that. And I have just marked that point on there as well to give some scale. Nice lots of 24s there. Okay, is this model likely to continue into the future? No. Basically with any population growth there tends to be something that's going to limit that growth in some way. So here with rabbits, the food will run out if there are too many rabbits. Some other external factor could start killing the rabbits, like humans could start poisoning the rabbits. There might be a new predator may come along and start killing the rabbits. There's all sorts of things that could happen. If that model was to continue into the future, after 500 months, that's how many rabbits there would be. What's that? That's 33 million rabbits. If we go even higher, plug in higher numbers for t, for months, you'll see that it gets ridiculously big pretty quickly. So if I put in some 9s there, oh, maths error, just too big for the calculator to handle. Okay, 7 times 10 to the 11 when I go into 999 months. In year 12, we will learn another model for population growth where the graph kind of it starts out exponential, but then something limits it and it comes up like that. But that will be not until year 12. In this example, we're going to look at what happens with something like caffeine in the human body. So caffeine, when you drink the caffeine, the amount of caffeine in your body will start to decay. It'll start to decrease. Your body will process the caffeine, and it will decrease according to this formula. So given that 1 cup of coffee contains 100 milligrams of caffeine and the half-life of caffeine is 5 hours, find the value of A. Okay, so our formula is C equals AE to the KT, and we find the value of K by letting T equal 0. So we were told that the amount at the beginning is 100 milligrams. So 100 milligrams equals AE to the K times 0. And of course, this is just 1, so A equals 100. In part B, we have to find the value of K. Now, to do this, you need to use this half-life information. So what they're going to do in these questions is they'll tend to give you amounts at 2 different points in time. So you use 1 point in time to make one equation. Usually they'll give you t equals 0, which makes it really easy. If they gave you like t equals 2 and something else at t equals 4, you might have to solve them simultaneously, which would be much harder. but usually they'll give you t equals 0, so you can find out A. Now, the half-life is the length of time it takes until the amount's halved. So in this case, the half-life tells us that after 5 hours, there'd be 50 milligrams left. Okay, so the C equals 100 e to the kt. The actual amount of, when t equals 5, C would equal 50. Because 50 is half of what it was 5 hours ago. So 50 equals 100 e to the k times 5. Now we just need to solve that equation. I'm going to divide each side by 100, but I'm also going to turn it around and write this on the left and this bit on the right. So I'm going to get e to the 5k, k times 5, I put 5k, equals half, because that's 50 divided by 100. I'm going to take the natural log of each side to undo this e. So 5k equals log of half. Remember from our log laws, I could write that as negative log 2 as well if I wanted to. And let's divide by 5. So k equals 1/5 of log half, or 1/5 negative 1/5 log 2. Those are both exactly the same. Now you were asked for 4 decimal places. This is what I would actually use in further working out. But to give it to 4 decimal places, that is negative 0.1386. And remember, if it's negative, that's because it's decreasing. It's decay rather than growth, and that's when you get a negative k value. So we need to find the amount of caffeine that would be remaining after 2 hours and the amount that would be remaining after 1 day. So now that we've got our k value, we can write our formula. It says 100e. Look, you could write this, but if you do, use a whole lot more decimal places because it can affect the rounding in your final answer. I'm actually going to use this one. So negative 1/5 log 2 times t. That t could have actually gone on the 1/5 as well. We could have gone t on 5 log 2. Anything like that's fine. And we want it after 2 hours. So 100e to the negative 1/5 log 2 times 2. Okay, I had a little glitch with my recording, so I'll just talk through what I've written over here. So I've divided each side by this part in the brackets, giving me t equals this. Make sure you put that in your calculator yourself, because it's a bit of a tricky one. Just make sure you get that same answer of 21.6 hours. Now, you can also press this button here to get it in hours, minutes, and seconds. Normally that's degrees, minutes, seconds, but it absolutely works as hours, minutes, and seconds as well, which is how I've got 21 hours and 37 minutes as my final answer.